Okay, so we looked at Tuesday, or on Tuesday, we looked at what happens if you start taking roots of complex numbers. So we've just seen with de Moivre's theorem what happens if you take a complex number and you raise it to higher and higher powers. Okay? We can now look at what happens if you start taking roots of complex numbers. And we started off by looking at this idea of roots of unity. Now, what did we notice about roots of unity? So for example, if I took an equation like this, how many solutions am I expecting there? 2, right? I'm expecting 2 solutions. And in fact, if I wanted to plot these on an imaginary grid, okay, so that would be real and that would be imaginary. If I wanted to plot these on my imaginary grid, here would my solution here be. So there'd be one over here at 1, and there'd be one over here at -1. So I have 2 solutions just like I was expecting. But then if I went ahead and had a look at solutions like this, so I look at an equation like this, x cubed equals 1. Well, the way which I solve this equation is I'm taking the cube root of 1. The cube root of 1. Just like up here, I was taking something like the square root of 1. Okay, so I'm starting to take roots of real numbers. How many solutions am I expecting with this type of equation? 3, excellent. So if I was going to plot these, here's my imaginary plane, sorry, my complex plane first. Okay, I'm expecting 3 roots. Does anybody remember where these 3 roots were located? Good, yeah, exactly. There's one over here at 1. There's another one over here, and there's another one over here. Now, what's the relationship between these 3 roots? Like, how do you know how far apart these 3 roots are? Exactly, yeah. You take the fact that they are equally spaced, a full term would be 2 pi, and you divide by the number of spaces between those roots. So in this case, there were 2 roots, there's 2 spaces. So therefore, they are spaced at pi radians apart, or 180 degrees. Okay? Whereas with this one, there are 3 spaces, which means that all of the roots are 2 pi by 3 apart. So in other words, the spacing between this one and this one is 2 pi by 3. The spacing between this one and this one is 2 pi by 3. And the spacing between this one and this one is 2 pi by 3. So it's really important to understand that the spacing between the numbers corresponds to the number of roots that you've got. They are always equally spaced. Okay, so if there's 3 roots, then there must be 2 pi by 3 apart. If I'm starting to solve an equation like this, okay, what's the spacing between those numbers? What's the spacing between those numbers? How many roots are there? 4, right? So I take 2 pi and I split it amongst 4 things. So therefore the spacing must be pi by 2. Yeah? So in other words, I have a root here at 1. I have another root over here at -1. Like, that's not a surprise. 1 to the power 4 is 1, and -1 to the power 4 is also 1. But then there's another root up here and another root down here, an imaginary 1, so I, and -I. Do you remember that? Okay, so the spacing between them is pi by 2, or 90 degrees, and so on. So it's important to understand that the spacing between each of these imaginary numbers, or each of these complex roots, will always be whatever 2 pi is divided by the number of roots. Is that okay? Are there any questions about that? No? Okay. So then we looked at what happened then if you have a different number here. So what if you didn't just use 1? What if you used, for example, 1 plus I? Okay, 1 plus I. And we asked them what would happen if we started taking square roots or cube roots or 4th roots of this thing here. Okay. So does anybody remember what happens? So what happens then if we start taking the square root of 1 plus I? It's taking the square root of 1 plus I. So effectively it comes from trying to solve an equation like this. You're basically saying that some complex number squared, I'm just going to call it w, is equal to 1 plus I, which means in order to find w, I need to take the square root of 1 plus I. It's exactly the same as what I was doing with my real numbers. So let's think about what happens then, because now the modulus of my complex number is no longer 1. In fact, what is the modulus of my complex number? What is the modulus of this complex number? root 2, isn't it? It's like root of 1 squared plus 1 squared, which is the square root of 2. So if I was going to plot this number in, so if I was going to plot 1 plus I in, it would be there. Okay, so there's 1 plus I. Okay. Now if I start taking roots of complex numbers, do you remember from de Moivre's theorem? That what de Moivre's theorem literally says is that I should say that my complex number, 1 plus I, written in polar form. Well, actually, could you write this in polar form for me? So what would 1 plus I be in polar form? Okay. You could write it in Euler form, but I asked for it in polar form. So root 2 cos. Excellent. Spot on. Okay. So now what happens then if I take the square root of this? Well, are you happy that taking the square root of a number is the same as raising it to what power? Good. It's the same as raising it to the power of a half. So if I follow de Moivre's theorem, what this literally means is I take this and I raise it to the power of 1/2. Yeah? And I also do n lots of this argument, so half lots of pi by 4, and then half lots of pi by 4 here. That's just de Moivre's theorem being applied here. Is that okay? Now something a little bit more than this, because we're expecting how many roots with this? How many roots are we expecting? 2, good. So we are expecting 2 roots here. We'll have a think about where they are in just a second, but I want to get the base one first. I want to get the base root first. So okay, this is my base root. This is my base root. So this is the square root. This is the square root of 1 plus I. If I tidy it up slightly, I get the 4th root of 2 multiplied by the cosine of pi by 8. You're happy that half times by pi by 4 is pi by 8, plus I sine of pi by 8. So if I'm going to plot this on my grid, here it is. I'm going to plot this on my grid. Here we go. It's there. Okay, so I've drawn 2 in there. We'll think about that in just a second. But are you happy that's where it is? That's where it is there. So literally what is happening here with de Moivre's theorem, you remember when you multiply by complex numbers, you get a stretch which happens, but also a rotation which happens as well. Is that okay? Yeah, like we saw that before. So you multiply by complex numbers, you get a stretch by a factor of whatever the modulus is, and a rotation of the complex plane by an amount of the argument. Okay? So what I'm doing here is by raising it to the power of a half, I'm literally shrinking that complex plane down. I'm stretching it inwards. Because you're happy by raising it to the power of a half, I'm basically taking root 2, that's the length of this thing, and I'm reducing it down. Okay? So that's the reason why I get a stretch inwards. In fact, if I'm going to plot this on here, I'd literally take this entire complex plane and I'd be stretching it inwards by root 2 to the power of a half. But I'm also getting a rotation which happens. And the rotation is half lots of the arguments. So instead of rotating it by pi by 4, I'm only going to rotate it by half as much. Hence, it will be occurring somewhere in here. So it'll be occurring halfway in here. Okay, and are you happy as well that I get a reduction in the modulus of the plane as well? So I'm getting a stretch inwards. Is that okay? Okay, so instead of it being an entire pi by 4 round, I'm now only going pi by 8 around. And the modulus of this thing is the 4th root of 2 instead. So I'm basically reducing it by root 2 to the power of a half. Okay, so the 4th root of 2. That is what I would call my base root. Okay, that's the hardest one to find. The other ones are easy. We're expecting 2. The other ones are easy. Once you've found the base one, all of the other ones just follow on from this based on what we just looked at with roots of unity. Okay, so how far apart do I expect my 2 roots to be? What's the spacing between my 2 roots? It's just pi, isn't it? Because my spacing would be 2 pi divided by the number of roots which I expect, which is 2. So that's my spacing. They're spaced pi radians apart. Okay? So if that's Z1, if you like, if that's my first complex root, my second complex root, that'll be Z1. My second complex root would be pi radians around, which would be over here. Is that okay? Like the angle between that one and that one is pi radians. Yeah? So that's Z2. So the spacing is still the same. This is what I say. If you're able to find the base root, the other roots fall out because you understand how they're spaced. Okay? So could anybody tell me, what would Z2 be? What would this root here be, written in polar form? Okay, so the fourth root of 2 still, so the modulus hasn't changed. But yeah, go on. Because of... Yeah, good. So I need to add pi to this. Okay, so it'll be 9 pi by 8. Jalher, you were going for the negative version. That's fine as well. That's fine as well. Just remember that it's always got to be measured from anti-clockwise from the positive real axis. Okay, so if you put a negative in, it means you're moving clockwise. Means you're moving in the other direction. Okay, plus I sine of 9 pi by 8. Is that okay? Like, these are my two roots. These are my two roots of complex numbers. So the process is actually really straightforward. The first thing I need to do is find the base root. And the base root is really easy. It's just simply using de Moivre's theorem. There is nothing surprising there. We've looked at that before. Finding the other root, people always stress about, but it's not difficult. Like, you understand that the spacing between roots should be 2 pi divided by however many roots there are. So the spacing between the roots should just be pi in this case. Okay, so all I've done here is I've taken this and I said, right, there's another root, pi radians further on, hence I get 9 pi by 8. Is that okay? Yeah?